Hello, everyone. Welcome back to the second workshop in the ICP Bitcoin DeFi Bootcamp. Today, we have our first technical workshop of the bootcamp, and that is going to be hosted by Moritz, who is here to deliver the intro to the Bitcoin integration. So I hope you're all here and ready to learn. For those of you who missed the first session, hopefully you've caught up on the recording. That was the introduction to ICP with Anthony. And hopefully you're ready today to get started on the technical integration. Moritz, thank you for joining us. Welcome.
Hi, everyone. Happy to be here.
Great stuff. So we can jump right in. There's no admin or announcements that need to be made today. So do you want to share your screen and we can get started?
Yes. So, everyone ready?
Yeah, looking good.
Let me actually remove this looks a bit better. Okay. Hello, everyone. My name is Moritz. I'm a developer relations engineer at Affinity. I think this is like the 5th or 6th time that I have the opportunity to present at an event that Encode Club is hosting. So very happy to be back. Maybe a bit about myself. Before I took the role of a developer relations engineer, I've been an ICP community member for a couple of years. So I think early 2018. Then I built a couple of projects on the IC, and then I thought the skill sets that I required would be a great fit for the role of a developer relations engineer. And as already mentioned, today I'm going to wait, let me check if this is the right presentation. It is. Title is confusing. Should be something different. Intro to Bitcoin integration. This looks a lot better. Okay. Yeah, so today I'm going to talk about the Bitcoin integration. Basically the flagship feature that you guys are going to use if you end up building BTC for applications on the internet computer. Throughout this presentation, there are many QR codes in the top right corner of the slides that you can either scan, or you just scan this one, which gets you the slide deck, and then you can either within the slide deck asynchronously scan the QR codes, or you can also click on the QR codes. They are all they all have a hyperlink attached to them, so you can get to the further reading material behind the QR code. So I give you maybe a couple of seconds to do that now, and then we can dive right in. Okay, that should be enough. So I know that if you already had a kind of like an intro session, but I still, for those that missed it, I still want to repeat a couple of the basics about the internet computer to make sure we are all on the same page before we dive in further. So if I would need to summarize the internet computer in one sentence, it would look like this. The internet computer is a decentralized and permissionless cloud built on blockchain technology. And we are going to work our way from the bottom of the tech stack up to the top. What you can see here on the slide is a so-called topology overview. So it depicts kind of like the architecture or topology of the internet computer. And we're going to start down here. Down here we see those black cubes. The black cubes represent data centers, and so-called node providers run their nodes within data centers. So as you can see, within each data center, there are, in this example, 4 nodes. Of course, it could be 100, it could be 10. Doesn't really matter. This is just like a simplification. And then the nodes, those gray boxes that you see here, they together form something that we call a subnet. And every node, as you can see here, can only be part of one such subnet. So the nodes are assigned to subnets, and they can only be assigned to one single subnet. And if you think about a subnet from a high level overview, a subnet is basically an independent blockchain. So it's a replicated state machine, and that means that every node within the subnet performs the same computation on top of the same state. And as you can see here, the internet computer consists not of a single, but actually many subnets. So in this case, there are 3, but in reality, I think we have roughly 50. And one thing that's special about those subnets is that they can seamlessly communicate with each other. And that in turn means that smart contracts that are deployed on those subnets can also seamlessly communicate with each other. And that is actually the magic that allows the internet computer to scale horizontally. So whenever we need more compute, more throughput, more storage, we spin up a new subnet to fill up with canisters, which is basically an acronym for smart contract. So when I say canister, what I mean is smart contracts, basically the same thing, just a different term. And a canister, just to be precise, is this, kind of like barrel that you see sitting on top of the subnets. And of course, a subnet can host many canisters. And you might ask, why do you call them canisters and not smart contracts? And that is because we want to be clear that canisters are an evolution of smart contracts as you know them. And I always think that it's easier to think about them as decentralized servers than traditional smart contracts. And the reason for that is that they have a couple of unique features and capabilities that you usually do not get when you deploy smart contracts on a blockchain. And those are the main features, the flagship features, and I want to go through them one by one. So the first feature that I want to mention here is timers. Timers allow you to execute specific logic either periodically or after a certain delay. So you could, for example, say, I want to execute this function in 5 years, or you can say, I want to execute this function every 5 minutes, or you could say, in 5 years, I want to execute this function every 5 minutes. And that's pretty cool because usually for something like this, you need off-chain infrastructure, but here this feature is provided by the system itself, and you can rely on the fact that those timers are actually being executed. The next feature is the so-called reverse gas model. Here, as the name suggests, the gas model is flipped upside down. So instead of your user having to pay gas fees to submit their transaction and for the transaction to be included in a block, actually the opposite is happening. The deployer of the canister, the deployer of the smart contract, charges the smart contract, the canister, with gas, and then that smart contract, whenever it's being invoked, pays for the cost of that invocation itself. So you subsidize basically the cost for your users. And it's great because it makes onboarding a lot easier because your users don't need ICP tokens or a wallet or need to know anything about Web3 or even need to be aware that this is currently being executed on a smart contract. Then we also have the opportunity to call into Web2 instances or servers, and that feature is called HTTP outcalls. And that's pretty cool because it allows you to, for example, call an exchange rate service to fetch the current Bitcoin price to build an oracle, or it also allows you to talk to, let's say, an RPC provider, for example, for an EVM chain to get information about the state of the chain or to submit maybe a transaction to that chain. We're going to talk about this in a little bit. Then we have a feature called web speed. This is a protocol feature that basically means that a canister executes, or the finality of the internet computer is, I think, roughly half a second, and the time it takes to execute a message end to end is roughly between 1 to 2 seconds. So if you think about it, if you build a dApp, and for example, someone wants to send a token from address A to address B, it takes roughly 1 to 2 seconds until that transaction has been finalized and executed. So that's very, very fast. So it basically gives you a web native experience. Then we also have on-chain randomness. So canisters can request secure randomness on chain. This is also something where you usually need some sort of oracle, some sort of off-chain oracle that feeds the randomness into your smart contract. But here, this is a protocol feature. Then we have chain key signatures. Whoops. Chain key signatures is very important today because the chain key signatures allow a canister to have control over a unique ECTSA or Schnorr key pair, and it also allows them to securely request signatures with the corresponding private key to be computed. What this means is that canisters can natively hold assets from other chains, for example, from Bitcoin or Ethereum, Solana, a lot of different chains, basically every chain that supports either ECTSA or Schnorr signatures. Then we also have big storage capabilities. So a single smart contract can currently store, I think, 500 gigabytes of data as of right now, with plans to enhance it to terabytes in the future. And it's not also only a lot of storage, it's also cheap storage, because a gigabyte of storage costs roughly $5 per year. So last time I checked, it was, I think, 80 million on ETH for a gigabyte of data, so orders of magnitude cheaper. And then another very cool feature is the fact that canisters can serve web. So you can take your front end that interacts with your backend, and you can deploy that front end in a canister smart contract as well. So you have your entire dApps stack decentralized and deployed on the internet computer, which of course helps with censorship and decentralization and not being hacked. Okay, so chain fusion. What is chain fusion? Chain fusion, this is a term you will hear a lot throughout the presentation today, is kind of like an umbrella word that is used to describe many things that are all aimed to fuse the internet computer protocol together with other chains and enable cross-chain functionality. And the idea of chain fusion overall is to leverage the different good properties of multiple different chains within a single dApp. So we want to bring the internet computer's strength to smart contracts on other chains and also vice versa. And as I mentioned, chains that are supported by chain fusion are Bitcoin, Ethereum, and most other EVMs or EVM-based layer 2s, Solana, and in theory also Cosmos, Sui, and others. So very, very broad support to connect or build with chain fusion on other chains or for other chains. But today you can see this like a tree. So we have the technologies, we have the applications, but today we are only focusing on those parts of this tree. So on the chain key signatures that we heard on the previous slide, to be precise, threshold ECTSA and threshold Schnorr, then on network integrations, in this case, the Bitcoin API, and then a bit on chain key tokens, which are basically synthetic twin tokens that are built using chain fusion. In this case, we talk about ckBTC, which uses obviously the Bitcoin API or Bitcoin integration. So I said chain fusion, get the best of all worlds, connect chains, and so on, but very abstract, right? So let's try to disassemble this. So what do you really need to integrate with another blockchain if you think about it, right? What you need to do is you need to be able to read state. So you need to be aware of, for example, the token balance from the, let's say, finalized state of a specific address. So how many ERC20 tokens does this user own? And you also need to be able to write to the other state. So for example, I want to transfer tokens on an ERC20 contract deployed on Ethereum, but that transaction should be triggered from a smart contract running on the internet computer. So two things, I need to read and I need to write. And of course, for most chains to be able to write, you need, first of all, to have the, let's say, canonical currency, which in the case of Ethereum is Ether. And to spend that currency, or basically to sign a transaction that is then being included in a block, you need to be able to create a signature, obviously. So those are the two building blocks. So I need to be able to securely read and write, and I also need to be able to sign transactions, because otherwise, how would I prove to the other network that, yes, indeed, the account I'm trying to spend from is really an account I'm authorized to spend from, basically an account that I own. So on the left-hand side, how can we achieve this to securely read from and write to other chains of interest? One opportunity or one possibility is to use the Bitcoin API. And how that works, we are going to find out in a couple of minutes. So if you want to talk to Bitcoin, use the Bitcoin API if you're building on the intercomputer. And if you want to talk to other chains other than Bitcoin, you can use HTTP outcall. So this feature I mentioned in the beginning that allows a canister to call into Web2 infrastructure. And what do we call into to read and write state? We call into RPC providers. And those exist basically for every chain. They exist for EVM chains. They exist for Solana. And to make this process less complex for our developers, we build abstractions around that are encapsulated into, let's say, public good smart contracts. And those are called one for the EVM chains, the EVM RPC canister, and another one for Solana, the Sol RPC canister. So if you're a developer and you want to read and write to EVM or to Solana, easiest way to do so is to talk to those canisters that abstract a lot of the complexity away from you. And of course, we're going to focus on the Bitcoin API here, and my colleagues will probably cover this part in more detail. And then if you want to build Bitcoin, the other thing you need is threshold, ECDSA, or threshold Schnorr signatures. And for this, you use the corresponding APIs. So Bitcoin supports both signature schemes, both ECDSA and Schnorr, so we can use both. If you want to learn more about other chains and how to integrate with them, feel free to scan the two QR codes here in the top right corner. So those are the three things that we are going to cover today when it comes to the Bitcoin integration and how to build BTC-Fi projects on the internet computer. All right. So I mentioned a couple of times, right, the Bitcoin integration, Bitcoin API, but what is it actually? In one sentence, the Bitcoin integration allows canisters on the internet computer to receive, hold, and send Bitcoin, and all of that directly with transactions on the Bitcoin network. So this is kind of like the high-level overview of what this thing does. Before we understand why this is so great, we have to look at how things used to work, or how things work most of the times, unfortunately, still today. And because we are talking about Bitcoin today, I thought a good example is to talk about wrapped Bitcoin on Ethereum. So let's look at how assets from other chains are usually made available on a target chain. So other chains, in this case, is Bitcoin, and the target chain, in this case, is Ethereum. So people at some point decided, hey, it would be great to have Bitcoin on Ethereum. But how does it work, right? Those are two different networks. So how did they do this? How does WebBTC work under the hood? When you're using WebBTC on Ethereum, you're actually trusting two groups of people. The first group are the custodians. They hold the assets. In this case, they hold the Bitcoin. And the other group are the merchants, and they are the only ones that are allowed to mint or burn WebBTC on Ethereum, basically to trigger mint and burn transactions on this smart contract. And even though I use the plural of custodians, in reality, it's a single company, and that company is called BitGo. So when it comes to the custody of the Bitcoin, you trust BitGo, a single entity, single company. So if you want to create new WebBTC that start to exist on Bitcoin, and therefore you want to bridge your Bitcoin to Ethereum, at first a merchant has to send Bitcoin to the custodian. As soon as the custodian sees that the Bitcoin have arrived, they mint the same amount of WebBTC to the merchant. if a user now wants to bridge their Bitcoin to RepBTC, they actually have to go through KYC and AML with the merchant, send them the Bitcoin, and then wait to receive back the RepBTC. If you want to go the other way around, so basically unwrap your RepBTC to BTC, then you again have to send the RepBTC to the merchant together with KYC and AML, and then wait to receive back the Bitcoin. And the RepBTC white paper even states that you have to trust the custodian not to run away with your funds, not to get hacked, and also to honor the one-to-one backing of RepBTC with Bitcoin. So what could happen? It could happen that BitGo decides, you know what, we're not interested in RepBTC anymore. The Bitcoin belong to us. We keep them. Goodbye. Or they get hacked and some nefarious actor actually steals their Bitcoin, which basically renders the RepBTC worthless. So you gave Bitcoin to receive a token that then is worthless because you cannot unwrap RepBTC back to Bitcoin. And it could also be that maybe this guy here with the cane decides, oh, you know, there are 100 Bitcoin in this bridge currently. I'm just going to take away 1 Bitcoin for myself. And then again, there's no one-to-one backing of RepBTC by Bitcoin. So in reality, your RepBTC is not really worth 1 Bitcoin, but less because there are only 99 Bitcoin in the bridge, but there are 100 RepBTC in existence. So those are the things that could happen that are, of course, not so great. And BitGo say to minimize the trust, the custodian cannot mint tokens on their own, but they need the initiation of a merchant to do so. But it should be fairly easy to find a merchant to collude with, to print money out of thin air if you really wanted to. And you also state that their framework minimizes trust as the credibility of the institutions involved is at stake. This is something I personally not trust my money with, but some people do. To summarize, this is a bridge, and the type of bridge is called a trusted bridge because you have to trust the entities that sit here. And there are certain assumptions with respect to the custody of the funds and also the security of the bridge in general. And the users also rely on the bridge operator's reputation, and they have to give up control over their assets. So basically, they will have to give up control over the Bitcoin. Okay, so this is the not so good, mainly status quo at this point in time. But thanks to the Bitcoin integration and the internet computer, things are in a lot of a better shape today, at least in our ecosystem. So again, what back to this term direct integration, right? What do we actually mean when we say a direct Bitcoin integration? So direct in this context means that there are no trust assumptions required other than trust in the correct functioning of the Bitcoin network, which you do anyways if you have Bitcoin, or which you have to trust if you have Bitcoin, and the internet computer. So in other words, there are no additional parties required, such as bridges or other types of intermediaries, resulting in a much cleaner and also more secure integration. So in essence, the difference between the existing solutions that we just talked about and the Bitcoin direct integration is that in the case of the Bitcoin direct integration, the actual funds are held by a smart contract directly, whereas solutions like RepBTC always have some level of trust involved. So you need to be willing to give away your assets and basically are at the risk of the custodian and the asset being hacked or turning rogue or something like that. So this is the main difference, that there's no centralized entity in this protocol level direct Bitcoin integration of the internet computer, which of course makes it very appealing to build BTCFi applications, because in DeFi, right, no one in their right mind would put like millions of dollars into a DeFi application where a single entity could just flip a switch and everything basically breaks or burns down. So that's why this is so important, and that's why this also enables real BTCFi and real decentralized applications that leverage the liquidity and the value currently to some extent still locked in Bitcoin. So it's a pretty cool technology. So what can you do with that? So you can use the intercomputer as a Bitcoin layer 2 to enable programmable Bitcoin. As you might know, Bitcoin doesn't really have smart contracts. It has a scripting language, but that is very, doesn't have a lot of features and doesn't allow you to build applications that you would be able to build on Ethereum. That's why there is no real DeFi on Bitcoin layer 1. And some of the examples of what you can do with BTCFi, which this whole workshop today, or the entire bootcamp, so to say, is about, is building BTCFi applications, like, for example, native Bitcoin borrowing lending markets. You can build on-chain smart contract wallets, so you can have a smart contract that controls Bitcoin on the Bitcoin layer 1. You could, for example, extract that away and send Satoshis via chat messages in a SocialFi application. You can actually build a DEX where people are able to trade runes against Bitcoin or BRC20s or ordinals or whatever. You can also create, of course, borrowing lending markets for Bitcoin meta protocols like ordinals, runes, and BRC20s again. You can build a neat thing that is called ckBTC, which already exists, which we are going to talk about a bit later. Smart contract managed BRC20 index funds, Deadman switch contract that escrows your Bitcoin, and many, many, many other things. Sky is the limit. It's basically up to your imagination what to do with this. So before we dive deeper into the inner workings of the Bitcoin integration, I want to make sure that we are all again on the same page and explain the concept of a UTXO a little bit. As a very simple example here, Alice on the left-hand side wants to send 400,000 Satoshis to Bob. And to do so, Alice has to consume 2 UTXOs. A UTXO is basically an unspent transaction unit. So a transaction unit that has not been spent yet. So she spends those 2 UTXOs, one for 100K and the other one for 300K, which adds up to the 400K that she wants to send over to Bob. So to do so, she creates a transaction with the 2 UTXOs that are being consumed as an input, and the new UTXO belonging to Bob produced as an output. So here are the transaction inputs, the UTXOs, and this is the transaction output that would belong if the transaction is being mined to Bob. And as you can see, those inputs do not start to exist out of thin air, right? They are actually outputs from previous transactions. So an output of a previous transaction basically becomes a UTXO that you can spend in a following transaction. So to create transactions on Bitcoin, you have to spend UTXOs, and you can obviously only spend the UTXOs that you own. Otherwise, I could just take your Bitcoin and send them somewhere else, which wouldn't be that great. So to enforce this, that you can only spend UTXOs that you own, every UTXO has a so-called public key associated with it. And you, as an owner, prove your ownership of the UTXO by creating a signature that is associated with the public key attached to the UTXO. The signature is depicted by this blue ribbon here. So here we basically proved using a digital signature that yes, indeed, we are authorized to spend this input as we own it. And then a lot of transactions are aggregated and put in a block. At some point, the block is mined, and the blocks that have been mined in the past line up or chain up to form what we call a blockchain. So this is a very high level explanation, but I wanted to make sure that we're all on the same page. So now with that out of the way, as we said in the beginning, 2 building blocks, right? Read and write and create signatures. And for reading and writing, we use the so-called Bitcoin API, which is enabled by a protocol level integration of the internet computer with the Bitcoin network. We remember no centralized bridge, right? No entities that you need to brush, just the internet computer and Bitcoin. So very secure and very nice. And what can you do with this Bitcoin API or the Bitcoin integration? It allows you as a developer to write smart contracts or to write canisters that are able to fetch the balances of certain Bitcoin addresses, the UTXOs that belong to certain Bitcoin addresses, And you can also get the block headers, fees, send transactions, and a couple of other things. So that is reading and writing, right? I can read, that is, I know the balance of an address, or I know the UTXOs that belong to an address. This is basically the only interesting read operations you would do on Bitcoin. And I can also write, because I have the capability to send a transaction to the Bitcoin network. But now the question remains open. Of course, as we just learned, I cannot just spend random UTXOs. I have to prove that I own them, and therefore I need a signature. And for this, we have the two signatures that are supported by Bitcoin, which are ECDSA and Schnorr. So we developed the so-called chain key signatures protocol suite, and that includes a couple of protocols, for example, for signing with ECDSA and Schnorr, but also it involves key generation, public key retrieval, and a couple of other things that are maybe not so relevant today. But yeah, with those two things, we have the two things that we need to integrate with another chain. And in this case, we have the two things that we need to integrate with Bitcoin. That's great. So we're going to start with the first building block, read-write, and that translates into the Bitcoin API. So to read and write, we use the Bitcoin API. To begin with, I quickly want to walk you through the functions that this Bitcoin API offers to developers that are writing smart contracts. What can you do? I mentioned already, but we're going through it again. So with this API, you can write a canister that can query against the full Bitcoin UTXO set. So we have the entire Bitcoin UTXO set sitting in a smart contract that you can talk to by interacting with this Bitcoin API. So you can write canisters that know about the held UTXOs and thus also the balances of any Bitcoin address out there. First thing, for this we use Bitcoin get UTXOs and Bitcoin get balance. So obviously this for the UTXOs and this just to get the balance. What we also can do, as we learned, is we can submit Bitcoin transactions. For this we use Bitcoin send state. The cool thing here is when you use this endpoint, what happens is that all the ICP nodes in the Bitcoin activated subnet directly transmit this transaction to Bitcoin network nodes without any need for intermediaries that might censor them. And that also has the effect that your transaction is distributed very broadly because you talk to a number of other Bitcoin peers at the same time. So that's a little bit of a benefit here if you use that. So of course, when you create a transaction, you have to set the transaction fee to the right amount. So for this, we use this Bitcoin get current fee percentiles. And last but not least, you can also request block headers from Bitcoin, and that allows you to do SPV, so simple payment verification. So you can have like a Merkle proof, and you can prove to the canister because it has the block header in a trusted way. You can prove, hey, this transaction really was included in that particular block. Okay, so those are basically the 5 functions that the Bitcoin API exposes that you need to read and write from and to the Bitcoin network. Pretty straightforward, I would say. But how does it work? How is this enabled? How does this magic come to life? For this, we have to take a little bit of a deeper look at our protocol implementation. And as you can see on this slide, the Bitcoin integration basically consists of 2 components. The first one is this Bitcoin canister that sits up here that I mentioned briefly, that lives on a so-called Bitcoin activated subnet. And it's basically just a regular canister, a regular smart contract that is controlled by the NNS. We unfortunately don't have time to talk about that, but maybe another time. And this Bitcoin canister holds, as I mentioned, the on-chain Bitcoin related state, and that is the full UTXO set, as we can see here, outgoing transactions, as you can see here, and the most recent Bitcoin blocks that allow for fork resolution. The other component is sitting down here, as you can see, very low in the stack, right? This is basically the application layer, so to say, and this is very low in the stack, which is the networking layer, and the Bitcoin canister, the Bitcoin adapter sits at the networking layer. And what does this adapter do? It connects two nodes that are part of a Bitcoin network, much like a regular Bitcoin node would do. And through this adapter, the internet computer can obtain Bitcoin blocks directly from the Bitcoin network. And of course, also process the contained transactions within those blocks. So let's go through it. How does it work that the canister can have, the Bitcoin canister up here, can have access to the full UTXO set on chain? So the way it works is that this UTXO set is managed by the Bitcoin canister and the Bitcoin adapter communicating through the internet computer's protocol stack. So this is the protocol stack, and those two communicate through this stack. And the process starts with the Bitcoin canister requesting successor blocks to the latest block it received from the Bitcoin adapter. And then the Bitcoin adapter, which runs on every node in the subnet, as you saw, there are many nodes in a subnet, and every single one of those nodes in the subnet have this adapter running. And then if the node or the adapter running on a node sees that the Bitcoin canister wants to see successor blocks to a specific block height, they then obtain those latest blocks from the Bitcoin network. They talk to Bitcoin nodes and they say like, hey, what blocks can you give me past this block height? The block making replica, or the block making node of this round provides the requested blocks that the Bitcoin canister requested, basically through consensus to the Bitcoin canister. So that way, the Bitcoin canister knows that the other nodes in the subnet also saw those blocks. So it can trust the blocks, and it can also trust the transactions contained therein. So once the Bitcoin canister now receives this block, it extracts the UTXOs from the transactions contained in the blocks and updates the UTXOs that it maintains in replicated state accordingly. And this is the mechanism that allows for maintaining the full Bitcoin UTXO set on chain on the internet computer. And it's also the same mechanism that is used to get block headers into the internet computer. And for the Bitcoin fee endpoint that I mentioned earlier, to decide what fee you want to set for your transaction, the last 10,000 transactions are being analyzed. And of course, this is a lot of data, right? To keep the full UTXO set, it's not a couple of megabytes or kilobytes, it's gigabytes. So the UTXO set itself has, I think at the moment, roughly 5 gigabytes. But of course, we need to do some indexing so we can efficiently query this set when you talk to the Bitcoin API and you want to get the UTXOs that belong to a specific address. There needs to be some indexing, otherwise this computation is too expensive and too slow. So with indexing, we end up having roughly 100 gigabytes of storage that is being occupied by this UTXO set. As you can see, this is something that is probably not possible on any other chain because the storage capabilities are just not there. But on the IC, we have 500 gigabytes of storage per canister. So Bitcoin could grow five times as much, and it would still work. Cool. Now that we know how all the functionality except for Bitcoin send transaction is enabled, let's talk about that as well. So if you as a developer want to send or write a smart contract that sends a Bitcoin transaction, it is first submitted from your smart contract to the Bitcoin canister. There, the Bitcoin canister queues it, and then every execution round, the Bitcoin adapter on each replica, this is the thing down here, obtains the transaction that you want to submit from the Bitcoin canister because they communicate through the stack, right? So it can read those transactions, and then every adapter submits the transaction to the Bitcoin network. So this is how the Bitcoin API works. This is the magic behind it. Let's move towards the second part, the signature creation, the chain key signatures, or you can also call them threshold signatures. And maybe as context, a threshold signature scheme is a signature scheme where the private key that you sign with is shared across a number of different entities, in this case, across the nodes of a subnet on the internet computer. So every node on a signing subnet has a small share of the secret key that you use to sign, for example, a Bitcoin transaction or other things. And I use chain key and threshold signatures interchangeably, so it's kind of like the same thing. And as we learned already, they come in two flavors. They come as threshold ECDSA and threshold Schnorr signatures. And what I mean by the secret key is shared across nodes in a subnet. So basically take the key, you split it up into so-called secret shares, and then every one of those shares is stored on a single node and on a single different node of the subnet. And if you want to create a signature with this secret shared key, that the nodes that all have their share, they have to coordinate to generate the signature that you requested in a distributed fashion. So in this case, at least a third of the nodes are required to jointly create the signature using their key shares. And through this, canisters have control, as I mentioned, over a unique ECDSA and Schnorr key pair, and they can request signatures with the corresponding private key to be computed. And you can also, from this key pair, basically every canister has kind of like a so-called, I don't know, like a master key, canister master key. And from this key, you can derive an unlimited number of keys. So it's not like a single smart contract on the internet computer has a single key and therefore a single Bitcoin address. No, they can control a vast amount of Bitcoin public keys and therefore addresses. So that's really cool. And one thing to remember is the private key that the subnet signs with never exists in reconstructed form, but only in its secret shared form, even when you're signing a message. So it's not like at some point all the key shares are together and someone can just steal them and sign. That's not how it works. And that's important to remember because this, would be bad, of course. And as I mentioned, right, those threshold signature schemes, ECDSA and Schnorr, they enable canisters to hold assets from basically virtually any other blockchain that supports those signatures, which is virtually any other blockchain. So every blockchain, I think, at least supports ECDSA or Schnorr to some extent. And how would it look like if you were to request a signature, for example, on a Bitcoin transaction that you created? I'm not going to go into the details here. You can read that if you follow the QR code, but basically we need two endpoints. One, to learn about a public key. And here, as I mentioned, it depends on the canister at root. It depends on the canister what kind of public keys I can derive. So every canister basically has its own tree of public keys that it can derive. And obviously, only the canister that sits at the root has control over the rest of the public keys that are in this tree. So canister A cannot create a signature belonging to the tree of canister B. That doesn't work. So you have a couple of arguments to, if you want to learn the public key, you provide a canister ID, which basically depicts the root of this tree, and then you can provide a derivation path. And this is basically determining in what place of this tree you want to get the public key from. That's maybe not the best explanation, but I hope you get the idea. So this is to get the public key. From the public key, you then derive the Bitcoin address, for example, or the Ethereum address or whatever. And then, of course, you need a method to sign a transaction that you created. And that is just by calling the sign with ECDSA endpoint. Here you hash the message that you want to sign, and you provide it as an argument to this method. And again, you can also use a derivation path. And as you can see here now, there's no argument canister idea. Learning the public key, the public keys of other canisters is of course no problem, but if you could sign for other canisters, that would be bad. So whatever canister calls this endpoint, this will be the canister ID that is used to then determine the signature that is being created. So to summarize, one endpoint to learn about the public key that a canister controls, or the public keys that a canister controls, and then another one to sign with the corresponding private keys of those public keys. And it's exactly the same thing, not exactly, but basically the same thing for Schnorr signatures, but I'm not going to go through that in detail, you can read the slide or again follow the QR code or ask me asynchronously. So now that we know reading and writing and we know creating signatures, let's look at a full theoretical flow that a canister developer could implement. It would start by, first of all, learning about the UTXOs that this canister owns or controls and that it can create transactions with, right? So this we find out by using this Bitcoin get UTXO endpoint that is exposed by the Bitcoin API. So the canister, as we saw, has many public keys, and in this case, it would take one of those public keys, convert it into a Bitcoin address format, and then call the Bitcoin get UTXOs endpoint to ask about the UTXOs that belong to this address that it controls. So now it has a set of UTXOs that it can use to create a transaction. So those UTXOs are, as we learned, the input to the transaction. And of course, it wants to make sure that the transaction is being mined, so included in the block. And therefore, it needs to learn about the current Bitcoin fees. And to learn about them, they use the Bitcoin current fee percentiles endpoint. Okay, so now we have the UTXOs and we know the fees. So this is enough for us to create a Bitcoin transaction. So we have some logic in our canister that now assembles this transaction. But the transaction is not going to be mined unless we can prove that we really own those UTXOs. So what do we need to do? We have to sign the UTXOs with the private key that corresponds to the public key that corresponds to the address that we used in this call. So we take our transaction and we, for every single UTXO that is contained in this transaction, we create a signature by calling either, depending on your setup, the sign with ECDSA or sign with Schnorr endpoint. And once we have that, we have everything that we need. We now have our Bitcoin transaction and we have signatures on the transaction that allow us to spend those UTXOs. So the remaining thing is, of course, to get this transaction somehow to the Bitcoin network. And to do so, as we learned, we use the endpoint Bitcoin send transaction to send the signed transaction to the Bitcoin network. And this is what happens in this step. So now the Bitcoin canister queues the transaction as being picked up by the Bitcoin adapter, and that again relays it to the Bitcoin network. And that's it. That's how it works. So to wrap up, I quickly want to mention ckBTC. And that is because depending on what you want to do, you might not even need this Bitcoin integration directly. You might be happy with just having a representation, a secure representation that does not require a bridge of Bitcoin on the internet computer to build DeFi applications around that. And that is maybe because the management canister APIs that expose the ECDSA and threshold ECDSA signing and the Bitcoin API, maybe they're too low level for you, or also maybe because for your use case, doing everything on Bitcoin layer 1 would be too slow or too expensive. Maybe your users don't want to wait an hour until their transaction is finalized. So a good amount of projects might just use ckBTC. And what is ckBTC? ckBTC stands for Chain Key Bitcoin. So as I mentioned, it's a synthetic twin token that represents Bitcoin on the internet computer, and it is built in a way that there are no centralized parties required. So there's basically no bridge. It's a bridgeless synthetic twin token. It's a new thing. So I'm not sure if there's a word for it yet. So the benefit, of course, of that is that it has a much stronger underlying trust model than the existing wrapped or bridged Bitcoin versions because of its decentralized architecture and because of the fact that it's built on top of chain fusion and the Bitcoin integration instead of centralized bridges. So as I mentioned, why you want to use it? Because it's easier to integrate. Instead of using the low-level Bitcoin API with Bitcoin get UTXOs, and you have to understand how to assemble a transaction and how to sign it and how to send it and how to make sure that it has been mined, blah, blah, blah. You might just want to use ckBTC if you just want to have a representation of Bitcoin. Because ckBTC is a so-called ICRC1 ledger. ICRC1 is a token standard. It's basically the same as ERC20. And so it's very easy to integrate with. It's widely supported, and it makes working with Bitcoin on the IC a breeze. Additionally, to the fact that it's easier to integrate with, ckBTC can be transferred with the low finality of the internet computer, obviously. So within 1 to 2 seconds, a transaction that you send with ckBTC is finalized. And it also costs you a fraction of what it costs on Bitcoin. Currently, a single transaction costs you 10 sats. So it's also feasible to do microtransactions, right? If you want to transfer, I don't know, 100 sats, that still put 10% of what you're transferring, but still it's possible, right? It's not like the transfer fee is higher than what you're actually transferring. Anyways, if you're using the scheme, ckBTC, the only settlement transfers, only the settlement transfers need to be executed on a Bitcoin network, and everything else is running on the intercomputer. So a majority of the transfers can be done with the lightning speed and the low cost of the intercomputer. And there are a couple of different components involved. There's the ckBTC minter that holds the Bitcoin on the Bitcoin network and mints and burns ckBTC on the ckBTC ledger accordingly. Then we have the ckBTC ledger, which is this basically ERC20 type smart contract running on the intercomputer. It's used to record the balances and facilitate the transactions and handle approvals and transfer forms and things like that. Then we have the Bitcoin canister. That is the canister that exposes the Bitcoin API, right? The ckBTC minter uses this canister to get UTXOs and send Bitcoin transactions. And then we also have the Bitcoin checker that makes sure that the ckBTC minter only has clean UTXOs and only interacts with clean addresses, so there are no OFAC complaints or something like that. And of course, when you send a transaction here, what's required implicitly is that you sign it in the first place by calling the sign with threshold ECDCA or sign with Schnorr endpoints on the management canister. So how would it look like if you go from Bitcoin to ckBTC? So the first thing you do if you have Bitcoin on the Bitcoin network and you want to get ckBTC is that you ask the ckBTC minter for a Bitcoin address that is reserved specifically for you on the Bitcoin network to convert Bitcoin into ckBTC. And it's based on your principal, which is basically an account if you're coming from the Ethereum world, and it's controlled by the ckBTC minter. So when you transfer your Bitcoin there, the smart contract now escrows the Bitcoin. And as soon as you have this deposit address, right, here you get the deposit address back, what you can do is you can transfer the desired amount of Bitcoin on the Bitcoin network to this address. Once that transaction is finalized, so after 6 confirmations, the next step is that you tell the ckBTC minter, hey, I sent you Bitcoin, give me ckBTC. And this happens through this update balance call where you provide the basically principal, your own principal and a sub account. The ckBTC minter then checks the address that it derives from this owner sub account. As you can see, this is the same here, right? And so it basically talks to the Bitcoin canister and asks, hey, did this user really deposit Bitcoin into the address that I gave him? And then the Bitcoin addresser in a happy path scenario says, yes, those are the UTXOs that I see for this address. And then the ckBTC minter for the new UTXOs mints you ckBTC on the ckBTC ledger by calling the transfer method on that ledger. And because the ckBTC minter, as the name suggests, is the minter authority on that ledger, a transfer basically corresponds to a mint that is new ckBTC start to exist. So this is how it works to go from BTC to ckBTC. The other way around is based on ICRC2, which is a token standard similar to ICRC1. It basically adds approval and transfer from two ICRC1 ledgers. And it first requires the user to allow the ckBTC minter to withdraw the desired amount from a user-controlled account by calling the ICRC2 approve on the ckBTC minter. So this is this call here. So here we say, yes, the ckBTC minter is allowed to spend this amount on my behalf without asking me again. Then we call the retrieve BTC with a pro endpoint to inform the ckBTC minter about our withdrawal intent. We basically tell it, hey, you can transact ckBTC on my behalf, and I want to get out of ckBTC into Bitcoin. And in addition to specifying the withdrawal amount, we also specify the address on the Bitcoin network that we want to receive the Bitcoin to. Then in the next step, the ckBTC minter tries to transfer the ckBTC on your behalf from your account. If that works, this, because it's a minter, counts as a burn, so those ckBTC tokens stop to exist. And then the retrieval request is basically put in a queue, and that queue, yeah, it's a bit difficult, but it uses a timer, and on a timer, the minter creates a single Bitcoin transaction that serves up to 100 Bitcoin retrieval requests. But yeah, we're not going to go into the details. So at some point, the UTXOs that belong to your withdrawal have been signed, and then the Bitcoin canister, the ckBTC minter sends this signed transaction using the Bitcoin send transaction API to the Bitcoin canister, and that again is then being forwarded to the Bitcoin network where it's mined, and then at some point you receive your Bitcoin. So as you can see, all of this is fully automated, right? There's no bridge or central entity or anything involved. It's just smart contracts running on the internet computer and the Bitcoin network. So it's secure, it's trustless, it's verifiable, and it's fast, and it's cheap, and it's great to build BTC-Fi applications. All right, if this caught your attention, I would very much recommend you to take a look at the website called bitcoindefi.dev. Here you can see a couple of successful BTC-Fi projects that build on the internet computer, namely Odin, Liquidium, and Omnity. You can also find specific primitives, best practices, and code examples to build or start building BTC-Fi applications. And I think it's the best way to continue learning and also to start experimenting with BTC-Fi on the internet computer. What I also want to encourage you to is to tune into the workshop series. So this bootcamp is basically split up into two series. The first one is kind of this educate series, where we, as you saw, talk about the concepts and the theory behind things. And then in a second phase, the workshop series starts after a bit of a break. And there we really do hands-on workshops. We really look at code and we build things, and the outcome is a bit of an example. So that you should bookmark. And this concludes my presentation. Let me look at the chat to see if there are some questions. There are also some resources here in case you want to learn more. The first one is a hackathon cheat sheet. That is a collection of great resources that are helpful, even if you're currently not participating in a hackathon. It's just a nice page to bookmark again. Then we have a developer forum in case you want to ask lengthy questions. This is a good place. We have the Bitcoin docs, right? We have a educate series that you did with Encode Club on chain fusion, where we focus more on the EVM side of things. If this is relevant or interesting to you, take a look at that. We have developer grants that we award. So if you are looking for non-dilutive funding, this is the place. And yeah, a couple of other resources as well. So let me quickly go to the chat.
We have had quite a busy chat. So I've been kind of making note of some of the questions that we've had. Are you able to hear me, Morris?
Yeah.
Yes, nice. So you can have a look at the chat now, but you might struggle to find some of the questions. So while you're looking, very early on, we just wanted some clarification as to what chains are supported by Chain Fusion, specifically whether Cosmos is or not.
Yeah, so supported can mean two different things. So in theory, Cosmos is supported as long as it supports ECDSA or Schnorr signatures, which, if I remember correctly, it does. That does not mean that there is this kind of like helper contract that we have for EVM, which is the EVM RPC canister, or for Solana, which is the Sol RPC canister. So that doesn't mean that you cannot integrate with Cosmos. It just means that it's more overhead for you as a developer. So you basically have to re-implement the, let's say, features that those helper or convenience canisters implemented already for EVM chains and for Solana. So it works, but you just have to build it. So it's more work and more overhead. But I'm pretty sure that there's a Cosm RPC canister. But yeah, I don't have the repository at hand now. Let's see. Here, okay. I actually found it. I'm not sure if this is production ready, to be honest. So, but it could at least serve as an inspiration. And yeah, that's that. So it works apparently. Otherwise, this repository probably wouldn't exist. But yeah, I'm not sure if it was audited or something like that.
It's got 3 stars, so looking hopeful. Okay, so another question we had was when you were discussing and explaining how UTXOs work, somebody asked, how does the ICP ensure that UTXO isn't spent before the operation is finished?
I mean, the ICP doesn't enforce it. It's the Bitcoin network that enforces that. So if you try to double spend, then yeah, you're trying to submit an invalid transaction, and an honest Bitcoin node would not include that in a block. And in general, as soon as there has been a new block added to the Bitcoin chain, the Bitcoin editor learns about it and forwards it to the Bitcoin canister, which then extracts the UTXOs and adapts its internal state accordingly. And because the block time or the finalization rate of ICP is a lot faster than that of Bitcoin, we can make sure that we are always at the latest tip or at the highest block height. So it's not, shouldn't happen that ICP kind of like lags behind when it comes to what blocks have been mined for Bitcoin.
Thank you. I think somebody asked earlier, I'm not sure if this was a question or a statement, but they said transactions on ICP BTC Fi, so Bitcoin Fi, they don't need confirmation unlike transactions on Ethereum. Is that true?
Can you repeat this?
So the statement is transactions on ICP BTC Fi, they don't need confirmation unlike transactions on Ethereum.
I mean, it depends on what this person is trying to ask. So if you create a Ethereum or Bitcoin transaction in a smart contract on the internet computer, sign that, and then submit that to your target chain, which would be either Ethereum or Bitcoin, then it would be just a completely normal transaction on that chain. That chain wouldn't know that the transaction was created and signed on the internet computer. That would be, irrelevant for it. So there the exact same rules apply for any other transaction that gets submitted to either one of those two chains. If you create a transaction for the internet computer itself that just targets a smart contract or a canister running on the IC, then this concept of confirmations doesn't exist in that form on the IC because we have a different consensus model than Bitcoin and Ethereum have. But it's a bit, it's a bit difficult to explain now in a short amount of time. But what I can say is that transactions on the internet computer or messages on the internet computer are also grouped into blocks, and they are going through consensus, and they are being finalized, and then they are being executed. And the time it takes to finalize a block that contains transactions on the IC is roughly a second, I think. So very fast. On BTC, there is like this probabilistic finalization where you say, okay, after 6 blocks, it's very unlikely that there will be a reorg. Yeah, but on the IC, they are finalized. They're not like probabilistic finalized. They once they are finalized, the chain will not change anymore. Yeah, hope that makes sense.
So I have just noticed that we've actually gone over time already. So everyone who has put questions in chat, thank you so much for engaging. I think a lot of them have actually been answered partly because the chat has been so active. So thank you everyone who's been answering questions throughout. And hopefully I did see the kind of discussion about L2s and their impact that they have on L1s. Moritz, you might want to read back through the chat after and you'll see the debate that was going on about halfway through the session today. If you want to continue that discussion, please do it on Discord. I know you were going to some quite interesting places before I interrupted you to focus us back on the session. But it's really cool to see you guys engaging in kind of thought processes like that. One last question, Moritz, before we wrap up, and thank you again for delivering this workshop. People have found it really, really helpful. Lots of compliments in chat as you've been going about your explanations on some topics like UTXO and stuff. But Jill has asked, are you looking for DeFi yield strategies for ckBTC? Yes or no?
Definitely. Yeah, definitely. I mean, I think this is the holy grail, right? Everyone is looking for that. Ideally, native Bitcoin yield, but that's a bit difficult because it has to come from somewhere, right? But yeah, I think a lot of people incentivize the, let's say, bridging or making Bitcoin available in their chain or in their protocol through providing yield, but that yield usually is not native Bitcoin or Bitcoin at all. It is usually another token that also has a certain value, maybe even the protocol's token that they give to people that deposit liquidity, Bitcoin liquidity into their protocol. But yeah, definitely something we are looking for.
Great. Jill thought the answer would be yes, but they wanted to hear you say it. So that is a great way to end the session today. So everyone, the link to the slides I put in chat earlier. We'll also post it on Discord after this, and I'll put the bitcoindefi.dev link as well. As for exporting the chat, Emmanuel, unfortunately you can't export the chat, but I do encourage you to continue it in Discord. If you're not already in the special Bitcoin DeFi Bootcamp channel, make sure that you join it through the platform. You should see a little Discord integration widget on the platform program page, and you'll be added to the channel specific to the bootcamp where you can continue this discussion. To those of you who struggle to get into the session today because of Livestorm asking you for an access key, the best workaround for that is to open your browser in incognito. We apologize for that issue. It does sometimes pop up when you sign in with your email address, but we suggest just signing in with your name. Don't log in through Microsoft or anything. Just literally sign in with your name, and you shouldn't be asked for an access key. But otherwise, please just open in incognito to clear cache. Thank you everyone for joining us today. I hope you've had a good session and you're going away with a lot of questions and things to think about. The recording for this session will be available tomorrow. Hopefully you'll only get one email this time telling you the recording is available. I apologize for the spam yesterday, but hopefully you are now fully aware that the workshop 1 recording is available, and this one will be available tomorrow as well. See you all next week for our next workshop, which is going to be on the introduction to the Solana integration. So make sure that you come to that with similar questions as you've had today, and we're going to have a really good time. Enjoy the rest of your week, everyone, and we'll see you around.
I want to add finally that make sure that you visit this bitcoindefi.dev website. I just scroll through the chat, but I think it would cover or answer a lot of the questions that have been asked. You might need to dig a little bit, but yeah, there's a lot of good stuff in there.
Perfect. We'll put the link in Discord as well, so you can access it after the session, everyone. Okay, cool.
Bye, everyone.
Have a good rest of your week.